Hey, what's going on, guys? We have the question right here. The question is asking an object on a spring oscillates with a period of 0.8 second and an amplitude of 10 centimeter. At t is equal to 0 second, it is 5 centimeter to the left of equilibrium and moving to the left. What are its position and direction of motion at t is equal to 2 seconds? So let's see how we can do this. So to find the position, we have to use this equation, that is x at t equal to a cos omega t plus phase constant. So this is the thing we have to use to find the position. So first of all, we have to know that this value we know already. Like, let's see. So first of all, if you check, we don't have the phase constant. We have to find the phase constant, and also we have to find the omega and amplitude. We know that it's given 10 centimeters, so we don't have to worry about that, but we have to find the omega and this is angular frequency and the phase constant. So let's see how we can find this. So first of all, we have the information that initial position is 5 centimeter to the left. So if it's left, it's negative, so this is going to be negative 5, and that is equal to, if it's initial, we use this formula for the position, that is a cos phase constant. So from this equation we can find the phase constant. So phase constant is going to be cos phi cos phi 0, and that is going to be equal to minus 5 over a. And also I can rearrange this equation. I have to find this one, phase constant, so I can take the cos to the other side. So this is going to be cos inverse minus 5 over a minus 5 over 10. Amplitude, we know this, it's provided right here, so we can write a is equal to 10, so this is going to be minus 5 over 10. And if I solve that, that will become cos inverse 1, cos inverse minus 1 over 2. So minus 1 over 2, it's mean cos inverse minus 1 over 2, so this could be plus or minus 2 by 3 5 radians, and that is equal to plus or minus 120 degree. So we found out the phase constant. So we have phase constant. Now we have to find the angular frequency. So let's see how we can do this. So we can use this equation, that is omega is equal to 2 pi over t, because we know the time, we know the period that is provided, that's 0.80 seconds. So we can use this to find the omega. So let's see, 2 pi over 0.8, and if you substitute these values, you will get 7.85 radians per second. So this is the angular frequency. So we can now substitute these values in this equation and find the position. So let's see how we can find. So we have a right here that is provided, that's 10, so we can substitute that one right here. Then cos omega is equal to 7.85 radians per second, and also they are asking the question when t is equal to 2 seconds. So we have to substitute that t for this t. So this is going to be 2 plus, we found out that phi phase constant is equal to 2 over 3 pi. 2 over 3 pi right here. So 2 over 3 pi, and if I substitute all the values and solve this, this one comes out to be 5 centimeter. So we have found the position right now. Now we have to find the direction of motion. To find the direction of motion, first of all we have to find the velocity, and from the sign of the velocity we can determine which direction it's going. So let's see how we can do this. First of all, we have to know the velocity equation, that is velocity is equal to minus omega a sine omega t plus phase constant, and if you substitute all the, we know all the values. Omega is here, we found out right here, omega, and a is 10 sine omega t. T is going to be 2 seconds, and then this is in the bracket and this phase constant. So if you substitute all the values, you will end up with plus 68 centimeter per second. Since the velocity is positive, the motion is going toward the right side. So that's the direction of the motion. So the direction is right side, because right side, because the velocity is positive. And that's how it's done. I hope you guys liked this video. See you next time.